SwayamPrabha. Digital India. Educated India.
So, what we had done in the last class, we were trying to find fluid dynamics inside human eye, and for that we had, because the dynamics inside the dynamics of fluid inside eye depends on the position of the eye. So, and it will depend on whether a person is sleeping or standing. We had considered a case where a person was sleeping, and in that case we were trying to find what is the dynamics of fluid. So, to summarize it, what we had done, we had taken that when a person is sleeping, the cornea will face towards vertically upward, and this is the iris surface which is at higher temperature because of flow of blood through this vessel, through the vessels in iris, and the temperature of this surface I had given as Th, which was equal to 37 degree centigrade, whereas cornea is avascular tissue and it does not contain any blood vessels. So, the temperature of this surface was Tc, which was slightly less than the body temperature, and we had said that it is, let us take it to be 33 degree centigrade, and inside in the region between cornea and iris, aqueous humour was present, and the aqueous humour flows because of the temperature gradient between these two surfaces combined with gravity, because buoyancy is there. So, that will make this fluid circulate inside the anterior chamber. After that, we had said that the dimension, because of the dimension we can use lubrication approximation, and the width of the anterior chamber we had taken as L, which was equal to 11 mm, and the depth of the anterior chamber is equal to B, and this is equal to 2.75 mm. Okay. So, this was our model problem, and after that we had wrote the governing equations and made it dimensionless. So, the dimensionless continuity equation came as dou u star upon dou x star plus dou w star upon dou z star equal to 0, and the x momentum, from the x momentum balance after lubrication approximation at the leading order you had gotten dou p star upon dou x star plus dou square u star upon dou z star square equal to 0, right. So, these were two equations which we had got yesterday. Now, let us non-dimensionalize z momentum balance. So, the z momentum balance we will write it in Cartesian coordinate system. So, this is rho naught times dou w upon dou t plus u dou w upon dou x plus w dou w upon dou z. This is equal to minus dou p upon dou z plus mu times dou square w upon dou x square plus dou square w upon dou z square plus rho times g, and this g is in z direction. So, I will write g z. So, now we will make the equations dimensionless. Before that, what I want to clear is, here we have rho naught, which is density at a reference temperature, which is constant, whereas here this is rho. And why I am taking like this is, so far in the course you have studied where the density was constant. You have whatever problem we had taken earlier in this course, in that course you have studied that density was constant, but here in this case the fluid flow inside the anterior chamber is happening only because the temperature is function of density is function of temperature, correct. So, that is why we cannot take density as constant, in this case. So, we will have to consider that density is varying, and that is why here you can see that I have taken rho, but here it is that there it is rho naught, whereas here it is rho, and this rho is function of temperature. The reason behind that, I should have taken at both the place rho as rho of T, but I have taken only rho as a function of temperature in the body force term, and the reason behind that is there is one approximation which is called as Buchnick approximation, which says that Buchnick approximation says that we can neglect the variation in density because of temperature in all terms except body force term, which is nothing but gravity here, when the temperature difference is very small. So, what I mean to say is, if the density difference between the two surfaces are very small, then we can take density as constant in all the places except in the body force term, and that is why you can see that in the inertial term I have taken density as rho naught, whereas in the body force term I have taken density as a function of temperature. Okay. Now, what I want to do, we will have to define that how density is varying with temperature. So, for that we will consider that this rho of T is rho naught times 1 minus alpha T minus T c. So, what it says that if the temperature is higher, then this density rho will be less than rho naught. So, as the temperature increases, the density decreases, and we have taken here that density is linearly dependent on temperature. There can be another case also, that density can depend on quadratic and cubic function of T also, this density can happen, but here we are considering in a simple way that density is a linear function of temperature. Okay. So, we will put it there. What this alpha is thermal expansion coefficient, and the value for this is a physical property. So, you will know this value of this parameter. So, here I will put that value of rho, and this will come as rho naught times this g will be minus g, because gravity is acting in negative z direction. So, it will be minus rho g into 1 minus alpha T minus T c. Yeah. So, I am replacing the value of that term with this term. Now, we will make it, now you can see that we have all the dependent variables in dimensional form. So, T is there, W is there, P is there. So, now I will try to make it dimensionless, and for that, because W is again present in all the terms on the LHS. So, I will take the characteristics scale for W as common. So, it will be rho naught time epsilon u, and the scaling factor for T is L upon u. So, u by L dou W star upon dou T star plus the scaling factor for u will come. So, capital U, for x it will be L u star dou w star upon dou x star, plus for w it will come epsilon times w, for z it will be epsilon times L, it will be w star times dou w star upon dou z star. Fine. So, this will be LHS term. If we will simplify it, we can see that u by L is common in all, sorry, this is u. So, u by L is common in all the terms. So, we will take u by L common and it will be rho naught epsilon u square by L square, and this whole term after taking u by L common will become Lagrangian derivative of w star. This is equal to, now we will have to make the RHS dimensionless. So, PC was I think mu u upon epsilon square L. Can you check it whether this was mu u upon epsilon square L or something else? Just check me and tell. I do not remember it exactly what it was. With the dimension it looks correct, into dou p star by dou z star. Can anyone tell me? It was this one. Okay, thanks. So, plus mu, again w is present in both the terms. So, I will take epsilon times u as common, and as done in the last class I am taking epsilon square L square common from denominator as I did for the x momentum. So, it will come as epsilon square dou square w star upon dou x star square plus dou square w star upon dou z star square. This minus, so I will write here rho naught times g times 1 minus alpha, and if you remember correctly, after defining the dimensionless temperature we had written that side that T is nothing but Tc plus Th minus Tc times T star. I remember this, you can check it in your notebooks. So, I will replace the value of T here. So, this will be Tc plus Th minus Tc times T star minus Tc, right. So, now you can see that this Tc will cancel out, and this term will be nothing but, yeah, I will write it here, this term I am writing only for this term will be rho naught g into 1 minus alpha Th minus Tc times T star. Okay. So, I will erase from this side now. Okay. So, what it will become, what I want to do now is I want to multiply both sides by epsilon q L square by mu u, the coefficient of pressure gradient term. Can I erase this also, because I want these equations to use further. So, I am not able to erase this one. Can I erase this one? If you have noted it down, I can erase. So, what it will become is I will multiply both the side with epsilon q L square by mu u. So, here it will become rho naught times epsilon times u square by, so this is L only, not L square, right, because L is only coming, L times, I am multiplying by epsilon q L square by mu times u, and this will be d of W star upon d of T star. This will be equal to, now the coefficient of pressure gradient will become 1. So, it will become minus dou P star upon dou Z star plus, am I missing anything, plus it will be here epsilon will cancel out. So, this will be mu u upon epsilon L square into, I am multiplying by epsilon q L q L square by mu times u, and this will be multiplied by epsilon square dou square W star upon dou x star square plus dou square W star by dou Z star square, right. And another term will be this one, which is plus rho naught g into epsilon q L square by mu times u into 1 minus alpha T h minus T c times T star. So, now here we will cancel some of the terms, u will cancel out, L will cancel out, here also mu u will cancel out, L square will cancel out. Yeah, so here it will become epsilon q times R e, epsilon to power 4 I think, right, epsilon to power 4 times R e, because epsilon q and this epsilon. So, epsilon to power 4 times R e into d W star upon d T star, this is equal to minus dou P star upon dou Z star plus epsilon square, because this q and this q will one epsilon will cancel out. So, epsilon square dou square W star upon dou x star square, I think here also epsilon square dou square W star upon dou Z star square plus this will become epsilon q. So, let me write it, it will become, what I can do is I will write it in this way. So, epsilon q I am taking common, and then rho naught I will multiply u in the numerator. So, that rho u upon L will become Reynolds number. Okay. So, what I am doing, so this will become nothing but epsilon q Reynolds number upon Froude's number, I will tell you how, into 1 minus alpha T h minus T c times T star. So, we have this term, what I am doing? I am doing rho naught times, I am multiplying u on the numerator, and L is already there upon mu. So, I have multiplied u in the numerator, so I will have to divide it also. So, here it will become 1 L will be there, and here g will be also there, and because I multiplied u in the numerator, so I will have to divide also. So, this u will become u square. So, this is Reynolds number, and this is 1 upon Froude's number, u square upon L g is Froude's number. So, that is why I wrote it epsilon q Reynolds number upon Froude number. Okay. So, what I want to do here is, this term has epsilon to power 4, and we know that epsilon is a very small quantity. So, this whole LHS will be very small, and they will not contribute to the leading order. So, this will be equal to 0. Similarly, here if we will come, this term will have epsilon to power 4 as coefficient, this term will have epsilon square as coefficient, and epsilon is very small. So, again the whole this term will not contribute at the leading order. Now, we will have here epsilon q R e upon Froude's number, this term should be 0 or not? Shall we neglect this term also at the leading order or not? We cannot neglect this one, because this is the temperature gradient that is causing flow inside the anterior chamber. If we will neglect this term also, we are neglecting the driving force. So, although we do not, because the magnitude of this coefficient will depend on Reynolds number and Froude number both. Although epsilon square, epsilon q r is very small number, we do not know the magnitude of Froude number. So, depending on the property, whatever scaling we have chosen, if we will calculate even the magnitude of Froude number, that will come as very small. So, this quantity, the whole quantity is not very small, and another so that is why we cannot neglect it. And another reason is like this is the term which is causing flow inside the anterior chamber. So, if you will neglect that only, we will get no flow inside. So, that is the another reason for not neglecting that term. So, from here we will finally get minus dou p star upon dou z star plus epsilon q re upon Froude number into 1 minus alpha Th minus Tc times T star is equal to 0. So, this is our z momentum equation. Now, we need to write another equation which is energy balance equation, because temperature is varying inside the domain. So, I will write it here, energy balance equation, and that is rho naught Cp times dou T upon dou T plus U dou T upon dou x plus W dou T upon dou z, that is equal to K times dou square T upon dou x square plus dou square T upon dou z square. So, this is our energy balance equation in dimensional form. Okay. So, now what I will do, you can make it dimensionless very easily. So, because T is this one, so dou T will be this temperature difference into dT star. So, it will be rho naught Cp times Th minus Tc, and everywhere it will be L upon U times dt star upon dt star. So, you will see that the scaling factor for T will come as U upon L, L will go up, so L upon U will come. Again from here U upon L will come, again from here epsilon U upon epsilon L will come, so epsilon will get cancelled. So, L by U will again come as common from all the LHS term. So, that is why L upon U is common everywhere, and because dt was there, so that is Th minus Tc into dt star. So, that is there, and on RHS it will be K upon again epsilon square L square I will take as common as I did for the x and z momentum. So, it will come as epsilon square dou square T star upon dou x star square plus dou square T star upon dou z star square. And you can send this term again to the LHS, and you will get something like here epsilon square Reynolds upon Prandtl number will come. It will come epsilon square Reynolds number upon Prandtl number times dt star upon dt star, that is equal to this term epsilon square. I will let me do it here, here only I will do, I will write it here epsilon square Reynolds number upon Prandtl number times dt star upon dt star, this is equal to this term. You can try it in your home and you will get it. So, again we will use the same funda, here epsilon square Re times Prandtl number is there. If you will calculate the magnitude of this will be very small. So, this will not contribute at the leading order. So, we will neglect this term, and here again epsilon square is there. So, this term will not contribute at the leading order. So, that will have also very small magnitude. and we are neglecting that. So, finally, we will get from here dou square T star upon dou Z star square equal to 0, and this is nothing but conduction equation. You have used it many times, even sir used it for when he was talking about freezing interface, that time also you got this equation, and this is a linear equation. So, the solution for this will be linear, and it will be T star equal to A times Z star plus B, right. So, we will have two unknowns A and B, and we have to calculate those unknowns using the boundary condition. And what are the boundary conditions we have here? We have boundary conditions as, so if we draw the schematic of model, so this was Th at z equal to 0, this was Tc. So, in the because these variables are dimensionless variables, so we will have to write the boundary condition in dimensionless form. So, if you will put T equal to Th, you will get that this will be Th minus Tc and Th minus Tc, so T star will be equal to 1. So, here at Z star equal to 0, T star is 1. You can put T equal to Th in that equation and you can see it, whereas on this surface, corneal surface, which is Z equal to H star, Z star equal to H star, temperature is Tc. So, if you will put here Tc, this Tc will cancel out, so T star will come as 0. So, we have T star as 0. So, using these two boundary conditions, we will calculate A and B. So, let us put T star equal to 1 at Z star equal to 0, from there you will get B equal to 1, and if you will put the boundary condition at Z equal to H star, from there you will get this T star is equal to 0 equal to A times Z star, there is H star, plus B is nothing but 1. So, from here you will get A as this is minus 1 upon H star. So, T star will come as 1 minus 1 upon Z upon H star, Z star upon H star, right? Yes. Oh, so you are saying that this surface, so B is 1, B this Z star will be 1 here only at that point, because that is B, else at all the places Z is changing. So, Z is a function of x here, this surface, that is function of x, and that is the value of Z is equal to B only at this point. So, I will give you the equation for that surface in some time, like we know the equation for this surface. So, you understand till this point that you know the equation of this surface, that is H star. So, we calculated T star, and you can see that temperature is linear function of Z. We cannot say that temperature is only function of Z, because the x dependency will come from H star. H star is function of x star. So, temperature is function of both x and Z. Okay, if you have any question till this point, you can ask. So, we calculated temperature now we have to calculate velocity and pressure. So, that is our main goal, that we want to see how the flow looks like inside the anterior chamber. So, temperature is linear in Z for sure. So, now what we will do, we have this equation for dimensionless equation which comes from Z momentum, this equation from x momentum, and here temperature is there which we have calculated earlier. Just now we calculated the function, this temperature, which is function of Z star and H star. So, now the unknowns are pressure and velocity. So, what we will do, as you learnt in when sir was teaching a stream function formulation, we know that pressure is a dependent variable, right. So, we always want to eliminate pressure from our equations in most of the cases, and that is why this stream formulation was created, so that the pressure will not come in the equation. So, in the similar way, what we have we will try to do, we will try to eliminate pressure from both these equations. So, we have this as x momentum, that from z momentum, and we want to eliminate pressure using these two equations. So, how can we do this? We will differentiate this equation with respect to x, we will differentiate this equation with respect to z. So, that is cross differentiation, and then we can subtract, so that this minus, that will become dou square p star upon dou x star dou z star, this will become also dou square p star upon dou x star dou z star, and if you will subtract, that pressure dependency will go away from these equations. Okay. So, let me differentiate it here with respect to x. So, this will become dou square p star upon dou x star dou z star plus epsilon q r e upon Froude number, and if you will differentiate with respect to x, the differentiation of 1 will be 0, this will be minus alpha T h minus T c, and here it will come dou t star upon dou x star. So, we have to differentiate this equation with respect to x star, and from here dou t star upon dou x star, that will be equal to 1 minus, the differentiation of 1 will be again 0. So, it will be minus z star, this is a function of x. So, it will be h to the power minus 1. So, that will become minus of h to the power minus 2. So, this will become plus, and the differentiation of h star will be h x star, here again it is star. So, that will be the dou t by dou x value. So, we will put that value here. So, this will become z into h x star star upon h star square, this is equal to 0. Right. So, what I did, we had temperature here in this equation, as we differentiated this equation with respect to x. So, here dou t by dou x will come, and we know temperature. So, we can get dou t by dou x from there, we substituted the value of dou t by dou x here from that equation. Now, we will differentiate this equation also with respect to z, and what we will get here, we will get here minus dou square p star upon dou x star dou z star plus dou q u star upon dou z star cube, that is equal to 0. Okay. So, now let me say that this equation is equation number A, and this is equation number B. So, we can subtract equation number A from B, and you will get here on the LHS you will have dou cube, let me write it here. So, what we did, we had energy balance equation, from that we calculated T star using the boundary conditions, and we substituted the value of T star in z momentum, we differentiated both the equations, and then we are subtracting it to eliminate pressure term from both these equations. So, if you will do this A minus B, if you will do, you will get dou q u star upon dou z cube, that minus this term, right, minus this term epsilon q r e upon Froude number into 1 minus alpha T h minus, sorry, alpha 1 is not there. So, this will be alpha T h minus T c times z times h x star upon h star square. This is equal to 0. Oh, so this is minus, right, because this is coming from gravity term. So, there minus g was there. So, this term will be plus, correct. So, this term was, this has g term. So, that was minus g because gravity was acting in the negative z direction. So, this has minus sign everywhere. So, after subtracting that will become positive. Okay. So, if you will simplify it, this will become, so what I am trying to do here, I will, okay, let me move this term on RHS and then we will simplify this term. So, all we are doing this to get u. So, from here we will get dou q u star upon dou z star cube, that is equal to minus epsilon cube R e upon Froude number into alpha into T h minus T c into z star into h x star, this is a star, upon h star square. And you can see that these quantities depend on the physical parameter, and T h minus T c is also constant because temperature we have said that it is 37 and 33. So, these are all constants. So, we will assume that this is nothing but k including minus sign. So, this will become nothing like k into h x star star upon h star square into z star. Okay. So, again you can see that on the RHS we have all these terms are dependent on x because h is function of x only. So, you can integrate it directly with respect to z and get u. So, let me differentiate one by one. Let me differentiate first time with respect to z. So, it will become dou square u star upon dou z star square. I am differentiating with integrating with respect to z. So, this will become k into h x star upon h star square into z square upon 2, and one arbitrary constant will come which will be function of x because we are integrating with respect to z. So, let us say that that is C1 of x. I will integrate it again with respect to z, and from here we will get dou u star upon dou z. So, what I will do, I can do it directly here, I can do it easily. So, this will be zq upon 6, right, because zq by 3 will come, 2 is already there. So, this will become zq by 6, this will become C1 z plus another constant, arbitrary constant will come which is a function of x. So, that will be equal to dou u star upon dou z star. And if you will integrate it again with respect to z, you will get u star is equal to k into h x star star by h star square into z to the power 4 by 24 plus C1 of x into z square upon 2 plus C2 of x times z plus z star, everywhere it is z star, plus C4 of x, oh C3 of x. So, we got u, but we have 3 arbitrary constants C1x, C2x and C3x in it. So, we need to eliminate those, replace those C1x, C2x and C3x using the boundary conditions. Okay. So, I do not need these equations now. So, what we did, we eliminated pressure by cross differentiation and we integrated the equation to get the expression for u, and we found that we have 3 arbitrary constants which are function of x. Now, to eliminate this we will use the boundary condition, and the first boundary condition is u star is 0 at z star equal to 0. Why this one? Because the lower surface, which is iris surface, that is solid wall. So, no slip condition will be satisfied on that wall. So, because of that u star is 0 at z star equal to 0. So, both the walls are solid walls, so they will satisfy no penetration and no slip conditions. So, if you will put this z star equal to 0 and equal to 0, you will get that C3 is equal to 0. So, C3 will be 0 here. So, now we have 2 arbitrary constants which we need to find. One is C1x, other is C2x, and what we can observe it, we have, although we have 2 arbitrary constants C1 and C2, but we have only one boundary condition for u, that is no slip on the upper wall, corneal surface. So, the upper surface we have u star equal to 0 at z star equal to h star. So, that is no slip on the upper surface. The first boundary condition was no slip on the iris surface. This second boundary condition is for no slip on the corneal surface, and if you will do so, you will get it to be 0 is equal to k hx star. Hx star is nothing but differentiation of h star with respect to x star, h star square z star to the power 4 by 24. So, z star is nothing but now h to the power 4 plus C1 x h star square by 2 plus C2 x into h star. Okay. So, from here you can get one relation between here h star is will come common, and because h star is not 0. So, we can set it send it to on the LHS, and from here you will get directly k into hx star upon. So, this square and this 4 will come cancel out. So, this will be h square, and again h will cancel out from that. So, it will be h star here. So, let me write it here again, k into hx star h star by 24, and this with minus sign is equal to C1 h star by 2 plus C2, and remember that C1 and C2 are function of x. Okay. So, we have one relation between C1 and C2, but we cannot find them separately because we have 2 unknowns. So, for that what we can do is we can use the continuity equation, because we have 2 boundary conditions left with W, no penetration condition at iris surface and corneal surface. So, we can use that to calculate this C1 C2. From continuity equation we have dou u star upon dou x star plus dou W star upon dou z star, that is equal to 0. So, from here you can get dou W star upon dou z star is equal to minus dou u star upon dou x star. You know the expression for u star which we have just calculated. We can put that and differentiate with respect to x, right. We have expression for u, we just calculated, which has C1 and C2. We can put the expression of u here, we can differentiate that with respect to x. So, the final equation will come in terms of C1 dash C2 dash. So, I think I have the expression for that, I will write it directly, and then you will integrate with respect to z. So, you will get W, because I am running out of the time. So, I will write the expression for W star. So, W star will come out to be minus of h xx star into h star by h star cube into k into z star to the power 5 by 120. You can try it at your room. So, it will come as C1 dash of x into z to the power 3 by 6 t j star plus C2 dash of x into h star sorry z star square by 2, and another constant will come which will be C4, which will be also function of x. So, we are getting constant over constants over constants. So, this is the expression for W. So, to calculate C4 we can use directly the no penetration condition at iris surface, which is W star is 0 at z star equal to 0, and if you will put z star equal to 0 in this, you will get C4 equal to 0. So, no penetration at the iris surface or at the bottom surface, you will get, using that you will get C4 x equal to 0. Okay. So, now this term is simply not there because C4 is 0. Now, we will use another boundary condition which is no penetration at corneal surface, and with that you will get 0 equal to minus. So, here you will put, we will do nothing but just we will put z star equal to h. So, you will get, okay, let me do here. So, this will be equal to 0 is equal to minus of h x star star h star by h star cube into k into z star to the power 5 by 1. So, z star is nothing but now h star by 120 plus C1 dash of x times h star cube upon 6 plus C2 dash x times h star square by 2. Yeah, you will get this one, and if you will cancel h star from all the equations, you will take common. Finally, you will get it to be, yeah, finally you will get, yeah, let me do it here only. You will get 120 h star x, here you will get h star square, and here you will get C1 dash h by 6, and here you will get C2 dash by 2. So, this will be your final equation after cancelling some of the terms. So, that is your one equation, this is your another equation, this is one, let us say that this is equation number 2. So, with these two equations we have to calculate C1 and C2. So, we have two equations, two unknowns. There you can see that you have C2 dash term, here we have C1 and C2 term. So, you differentiate equation 1 with respect to x, this equation. So, you will get equation in C1 dash and C2 dash, right. So, that equation will come out to be, I will write the equations directly. So, that equation will come as C1 h by 2 plus C1 dash h by 2 plus C1 into h dash by 2 plus C2 dash, this will be equal to minus k by, so minus was here, minus k by minus k by 24 into h x star into h star. So, this is equation number 3. So, from equation 2 and 3 you can see that here you have C2 dash, there you have C2 dash by 2. So, you can divide this equation with by 2 and you can subtract it. If you will do so, you will get a equation in C1 dash, right. Here we had h x x star star into h minus 2 times h x star square over 120. So, this is, I think this is what you are saying. Yeah, that will be there, I forgot that term. So, this minus 2 h x star I had forgotten, that will be there in the equation. So, with these two equation you can calculate C1 dash. So, I will write the equation what you will get. So, what you do, you divide this equation by 2 and subtract 3 minus 2. So, then you will get a equation, I will write it directly. So, after doing equation 2, equation 3 divided by 2 minus equation 2. So, if you will do this operation, you will get equation which will be two C1 dash h plus 6 C1 into hx star star, this is also star, equal to minus 3 k by 10 into 3 h x star star square plus h star into h x star star. So, you will get this equation, and this equation is nothing but just one ODE in C1. So, by integrating this, or you can solve it in Mathematica or anywhere, you can get the solution for this, because you know h of x. So, from here you will get C1 of x, C1 of x you will find from here, and you put in this equation to get C2. Yeah, you put in this equation to get C2. 3 more minutes. So, from this equation you will get C1, you get C1 and put in this equation to get C2. So, C2x will be known to you, and these were the only two constants which were unknown to us. If so, I will write the equations, the expression for C1 and C2. So, you will get it to be 3 k x star upon 5 into 1 minus 4 x star square to the power 1 by 2, and C2 x will come as minus 2 k x star divided by 15. So, this you will get for C2. One additional thing is, to solve this equation you will need h star. So, that I will write it here, what is the expression for h star which I am taking, the equation of corneal surface. So, this h star is, so h which is in dimensional form, so h is b into root under 1 minus x square by a square. So, this is in dimensional form, and if you will make it dimensionless you will get as h star is equal to root under 1 minus 4 x star square. So, you will have to put this h star here and solve this equation. So, by doing so you will get u and w, and you can plot the stream function. So, this is the last of the this class. So, what I want to say you that how the flow will look like, because that was our motivation for doing this problem. So, this was at Th, this surface was at Tc, and aqueous humour was starts to flow because of the temperature gradient. So, using this u and w, because you have calculated C1 C2, you will get u and w. If you will plot the stream function, you will get circulation like this. So, this is your center line, and this will flow like this. So, why this looks like this? Because here the temperature is higher, so the fluid near this surface will rise up, and it will rise up and it will hit the cornea. So, it will have to move around the cornea, because that is solid wall. So, it will go up, it will move around the walls of cornea, and again it will come like, and the circulation will look like this. Again the other thing is the flow pattern will be symmetric about z equal to 0, x equal to 0, that is because the modal problem is symmetric. So, that is why. Okay. This transport phenomena course is not limited only for solving flow through pipes, flow on the over the plates and all. You can solve the realistic problem also. So, this is something like flow inside a eye, that is very complicated problem related to biological things and all. So, you can although the mathematics will be slightly tough and lengthy, but you can solve the realistic problem using transport phenomena course things. Okay.